So I'll start out talking about novae and X-ray bursts, and then talk about some of the measurement techniques that we have to measure the reactions that occur during them, and then talk a little bit more specifically about GODDESS and two of the reactions that we measured with GODDESS to constrain some of these reactions. And then switch gears sort of at the end and talk a little bit more in depth about a new gas jet target that we're building called Solstice. And so starting out with the introduction, at the end of a star's life cycle, most stars will either become a white dwarf or a neutron star, depending on the initial mass of the star. So for stars like our sun, with a mass less than about 8 solar masses, these stars will eventually become white dwarfs with a upper limit for the mass of about 1.4 solar masses, which is the Chandrasekhar limit. Masses that are heavier than about 8 solar masses will become neutron stars or a black hole. The neutron star itself has an upper limit of the mass of about 2.5 solar masses. And I have this question mark here just based on the recent gravitational wave measurement that found either the heaviest neutron star or the lightest black hole at about 2.6 solar masses. Nevertheless, neutron star radii are on the order of about 10 to 15 kilometers, which makes them more dense than that of the nucleus at about 10 to the 17 kilograms per meter cubed. And to kind of put that into perspective, if you took all of the humans on Earth and condensed them down into some sort of human star cube, this cube would have dimensions right about the size of a 2x2 Lego brick, which I find somewhat amusing. And so you can get, even though these stars are at the end of their life cycle, you can still get reactions occurring on them, especially when they're in a binary system with a less evolved companion star. And so in these cases, the less evolved companion star has filled its Roche lobe, and which allows material to then flow through the Lagrangian point onto the white dwarf of the neutron star. And so the events that you get on white dwarfs are called nova explosions, and here the material that's generated gets expelled into the interstellar medium, whereas for X-ray bursts, which is a very similar mechanism on the neutron star, the material that's generated is not expelled just due to the high surface gravity of the neutron star and makes up the crust of the star. And so observations of these events are extremely important because they help us to then constrain the nucleosynthesis occurring and, for example, the mass-radius relation, the star composition, among other things. And so what are the isotopes that are created during these events? These isotopes are on the proton-rich side of stability here, as you can see in red. Really what we're doing is starting in the hot CNO cycle, as you can see down here, and then breaking out of the hot CNO cycle via P gamma, for example, alpha P or alpha gamma reactions, up to the alpha P and RP processes. In general, novae generate nuclei up to about mass 40 down here, and X-ray bursts up to about mass 100 up here. So the two reactions that I'm going to talk about in the middle of this talk are important for nova explosions, so I'm going to focus down a little bit more specifically on novae. Novae in general, though, are extremely interesting because many of them are detected each year. And so, for example, if we could detect gamma rays from the nuclei that are decaying after the explosion, this could help us to constrain nova nucleosynthesis. And there are a whole bunch of different reactions that are important that influence the abundances of these stable isotopes that are created. So sensitivity studies have been done, and I'll just point out one that was done by Iliadis et al. In 2002 that identified a whole bunch of important reactions for nucleosynthesis. And so this is the table that they kind of came up with down here. And I just point out two of the reactions here because these are the ones that I'm going to be talking about in a few slides. And we actually just published a new PRC for an 18P alpha reaction that just got accepted yesterday. But what do we need to constrain these reaction rates? While it would be really nice if we could measure these reaction rates directly, however, these are extremely difficult to do, especially in the correct temperature range, which is the gamma window, which is just the intersection between the Maxwell-Boltzmann distribution and the probability to tunnel through the Coulomb barrier. So here your cross-sections are extremely low, which makes direct measurements extremely difficult, as well as you might be constrained, for example, by your beam or target availability. Reaction rates that proceed through resonances, you can also just calculate from the properties of these resonances, and you can get information on these properties from indirect measurements as well as direct measurements. And so here you need, for example, the resonance strength, which depends on the spin parity and the proton widths for the different levels. And probably more importantly is the resonance energy, which comes in exponentially here in the reaction rate equation. And here you can obviously get this from direct or indirect studies. And so just to give you a quick idea of what I'm talking about when I say direct and indirect, indirect measurements, as I mentioned, are necessary, especially in cases where the intensities, for example, of your radioactive ion beams are low, or you have low cross sections of the gamma window. And here you're focusing on measuring resonance properties via, for example, DN, DP, or helium-3D, or gamma ray spectroscopy, for example, from fusion evaporation. One of the devices, or two of the devices, I guess, that we have to measure some of these reactions are GODDESS and ORRUBA, and I won't spend too much time on them here because I will be talking a little bit more specifically about GODDESS in a couple slides, but just to give you a general idea. Or you can measure these reactions directly, for example, with recoil separators like SACAR at MSU, Dragon at Triumph, or St. George at Notre Dame, which use a gas target to do these alpha-induced and proton-induced reactions. And here you're separating the recoils from the beam through a whole bunch of magnetic and electrostatic elements. So you can see SACAR down here at the bottom. Or another way that you can get some of this information is by using an active target like music, anison, or the ATTPC, and you fill your volume with gas here and then use that as the target. And here you're able to measure total cross sections across a really large energy range, which makes them extremely useful. I'm sorry if your favorite device isn't listed here. This is just a quick snapshot of some of our capabilities. Okay, so switching gears now and talking a little bit more specifically about GODDESS. And to motivate this section, we need to take a step back and think once again about nova explosions and the reactions occurring there. So as you're looking at the hot CNO cycle, two of these isotopes maybe stand out to you a little bit, one being nitrogen-13 and the other being fluorine-18. And these two isotopes are important because we think that they could be important gamma ray emitters, and so we might be able to measure the gamma rays from these when they decay after the explosion. So here's just a list of probably the most probable gamma rays that we might be able to see from a nova explosion. Fluorine-18 in particular is really interesting because its almost 2-hour half-life means that it will be able to survive in the envelope of the explosion until the explosion envelope becomes transparent to gamma rays. Its half-life is also short enough that we will be able to attribute it from a specific nova explosion if we detect the 511 keV radiation, as opposed to something like aluminum-26 that has a million-year half-life. And so fluorine-18 beta plus decays, meaning it will produce a positron, and that positron will eventually annihilate an electron and create annihilation radiation. The problem here is that fluorine-18 is also destroyed by proton capture reactions, and the fastest of these is the fluorine-18p alpha reaction, where fluorine-18 captures a proton, creating neon-19 in some excited state as the compound nucleus, which then decays or disintegrates into O15 in an alpha particle. So we really need a good understanding of the fluorine-18p alpha reaction rate so we can accurately predict what the flux of this annihilation radiation should be. And we haven't actually detected this radiation directly from a nova explosion yet. So what do we need to calculate that 4818P alpha reaction rate? Well, we need information about the level structure of neon-19. So the most important resonances here that we're looking at will be correspond to 3s plus and 1/2 plus states in the neon-19 nucleus. And so one of the most important states is up here at about 7 MeV, which has a spin parity of 3s plus. This state's important because it's broad, meaning that any other 3s plus states near the proton threshold, down here at 6410 keV, will interfere with this state and therefore make the reaction rate more uncertain. And we think that there should be a couple of 3s plus states down here, just based on the structure of the mirror nucleus, 4819, that has 2 3s plus states at about the right energy. And so if we take a look at the S factor, which is just the cross-section with the Coulomb portion of that removed, you can see that our really broad resonance here, and the potential 3s plus states down here closer to 0 center of mass energy. And the unknown signs of the interference for or between these levels greatly increases the uncertainty in the gamma window. And so there have been a whole bunch of studies that have tried to look for these 3s plus states near the proton threshold. The first was by Utku et al. In 1998, who found 2 levels using the fluorine-19 helium-3T reaction. And here, these 2 levels are the same ones that I show over here in the level scheme. And they assign spin parities of 3s plus to both of these levels just based on the level structure of fluorine-19. Subsequent measurements, however, have not been able to find or confirm these 3s plus states. And so their energies are still in question. And as I mentioned before, the energies are extremely important to constrain. And so to try and search for these levels, we decided to use GADAS, which is the Gammasphere or Retina ORRUBA dual detectors for experimental structure studies, where ORRUBA is the Oak Ridge Rutgers University barrel array of silicon detectors, as you can see right here. And we're placing that inside of a gamma ray spectrometer like Gammasphere Retina, which in total makes up basically a 4 pi particle gamma spectrometer. So in total, you have something like 720 channels of silicon here between the barrel and the end cap detectors, with about 1 degree angular resolution, which is really great. And so as I've mentioned a couple times, we measured the fluorine-19 helium-3T and calcium-40 helium-3 alpha reactions. And so just talking a little bit more specifically about these 2 measurements, and I say 2 measurements, they're actually the same measurement, just different reaction channels. And so when I talk about the calcium-40 helium-3 alpha reaction, I won't actually go through the setup again. Just keep in mind that it's basically exactly the same. In general, we had a helium-3 beam delivered by the ATLAS accelerator at Argonne to our calcium fluoride target. And the tritons and alphas were detected in the downstream portion of the ORRUBA barrel here, in coincidence with gamma rays from the decay of the calcium-39 and neon-19. And so if we take the energy that was detected in the thin detector versus the energy detected in the thick detector in these telescopes, we can really nicely separate out the different reaction products that were created during the experiment. So this is an example for the barrel detectors here. And then for the end caps, you get a very similar looking spectrum like this. And as you compare these 2, you might notice that we didn't actually see the helium-3 or helium-4 in the end cap detectors. And that's because we put an aluminum plate in front of these detectors. So in the calcium-40 helium-3 alpha reaction, we actually only use the barrel. So if you take your tritons that you're detecting from the telescopes and you convert those energies back into neon-19 excitation energies to see what was populated, you get a spectrum that looks something like this, where you can see that our resolution here isn't the best, and that's mainly due to that aluminum plate. This is a spectrum from the 555 end cap detectors. But this doesn't really matter too much because we're trying to ultimately get the energies from the gamma rays. And so just going through the analysis that we did here just a little bit, one thing that we needed, that we decided we needed, was a Doppler correction. And as a naive grad student, I didn't think at first that we would need a Doppler correction because we were measuring this reaction in normal kinematics. And I expected then the neon-19 wouldn't have enough energy for it to really matter. As it turns out, it does for most of the levels in neon-19. And I say most because it really depends on the lifetime of the state that you're trying to look at. So for example, for this 1507 keV state, which has a lifetime of about 1200 femtoseconds, you can see that this state doesn't need a Doppler correction. So this is an uncorrected spectrum. This state doesn't need a Doppler correction at all because the neon-19 has enough time to lose all of its energy in the target and stop before it decays. Whereas for the 1536 keV state, which has a lifetime of only 16 femtoseconds, the gamma rays from this state will be Doppler broadened because the neon-19 still has that kinetic energy. And so in general, the neon-19 kinetic energy range from about 0.5 to 4 MeV, where beta, the velocity over the speed of light, range from about 0.005 to 0.025. And so we were able to calculate this correction individually for each event, just based on the triton energies and angles that we detected. So just to give you an idea, the energy resolution for the 1298 keV gamma ray improved from about 3% to about 0.7% after the correction. And if we take a look at some of these higher energy gamma rays, we can see what effect this Doppler correction has on these spectra. So for example, for this decay from the 4603 to the 238, before the Doppler correction, you might have thought that maybe there were 3 gamma rays here, but after the correction, it turns out it's just this one here. So this Doppler correction was really necessary, and actually necessary essentially for all of our gamma rays that we detected. So we use coincidences between the tritons and gamma-gamma and triton-gamma coincidences to build up the neon-19 level scheme. So in total, we found 41 transitions, with 21 of those transitions being previously unobserved, which are the ones in red over here on the left. Of note, for the fluorine-18p alpha reaction, we found 2 levels above the proton threshold, one at 6423 and one at 6441, both plus or minus 3 keV. And the observed gamma decays from these 2 levels look like those 2 3s plus states in fluorine-19. So just to go through that here, over on the right-hand side, I have the level scheme from neon-19 and the level scheme from the mirror fluorine-19, showing all of the important levels for this discussion. And so over here on the left, you can see once again our triton spectrum, and this shaded region then corresponds to the region that we gated on to generate all of these spectra that I'm about to show. But stepping through these just quickly one by one, the first decay is this 6200 keV decay from the 6441 to the 238 5s plus state. And you can see that I also populate this one on the fluorine-19 level scheme as well. The next is this decay to the 1616 3s minus state from the same level. Next up, we have this decay to the 275 1/2 minus state, which actually comes from both of the 3s plus states in fluorine-19. The next also comes from both of the 3s plus states in fluorine-19, and this is the ground state, even though we only saw it from the one in neon-19. And finally, this decay to the 1508 keV state in neon-19, which is a 5/2 minus state. That's only seen from this one, from the 6497 in fluorine-19. So in general, we found at least one example of all of these gamma rays. The only one that we didn't see is this decay from one of the 3s plus states to this 3 minus state, which in neon-19 is at about 4600. Unfortunately, the energy from one of these 2 levels, if it did exist, the energy of that gamma ray would have really nicely overlapped with another intense gamma ray at 1840 keV from neon-19. And the level that's producing this 1840 keV gamma ray was actually the only other level in the N19 besides this state at 1500 that didn't need the Doppler correction. And so what ended up happening was once we Doppler corrected, this 1840 just got smeared out, which meant that we couldn't actually see these. But in total, just looking at these 2 3s plus states look very similar, at least in the decays that we found, to the 2 3s plus states in 4 and 19. So we can go ahead and use these 3s plus states and see how constraining these energies then affects the 4 and 18p alpha reaction rate. So looking once again at our S factor calculation here, you can see that the unknown sign of the interference in the gamma window, which is somewhere down here, is still a very important factor here. But to calculate the S factor and the reaction rate, we needed information about the proton width, which we didn't actually measure in this experiment. And so what we did was took the proton width measured by, or estimated by Adicola et al. In their 2011 measurement using the 4 and 18 DN reaction. In that measurement, they estimated the upper limit for the proton width for a level at about the right energy to be 2.35 times 10 to the minus 15 keV. So in general, we assumed that basically this entire proton width was in one of the 2 3s plus states. And so we calculated the S factor and the reaction rate with the R matrix code as 0.2, excuse me, and the energies of the neon 19 levels were then buried within the uncertainties to produce uncertainty bands for the reaction rate. And so we needed something to compare this to, and since these 3s plus states hadn't been actually confirmed before, we decided to estimate the energy for these levels from an estimation made by Nezaraja et al. Paper, where they estimated the level shifts from the mirror for a 19 nucleus to be 50 plus or minus 30 keV. And so these are the 2 energies that you end up getting when you do that, 6447 plus or minus 30 and 6477 plus or minus 30. And so in general, you can see that by constraining the energies of these 3s plus states, you end up reducing the upper limit of the 4 and 18p alpha reaction rate by about factors of 1.5 to 17 in the temperature range of nova nucleosynthesis. So we also went ahead and decided to take a look at how this affects the abundances of the 4 and 18. And so to do that, we did calculations using the computational infrastructure for nuclear astrophysics via a multi-zone nova simulation on 4 different white dwarf masses. To do this, we parameterized our 4 and 18p alpha reaction rates and combined them then with the other reaction rates in the ReactLib database that were needed for the network. As you can see on the bar chart I have over here, we significantly then reduce the uncertainty in the 4 and 18 final abundances when we constrain these level energies, which is essentially the difference between the dark bars and the difference between the light bars here. Where the average reduction in abundance range was about a factor of 2.5 on average. Okay, so switching gears once again and now talking more specifically about the calcium-40 helium-3 alpha reaction. So we measured this, we decided to take a look at this reaction channel because the levels in calcium-39 are resonances in the potassium 38p gamma reaction rate, which is up here. This reaction rate is important because it affects the final abundances of argon 38, potassium 39, and calcium 40, these stable nuclei from nova explosions. And currently there's an order of magnitude discrepancy between what we expect from our models and what has been observed. And so the thought is that if we could understand this reaction rate a little bit better, we might be able to resolve some of those discrepancies. So as I mentioned, the resonances for this reaction correspond to states in calcium-39 above the potassium-38 plus proton threshold. And the most important levels here will have spin parities of 5/2 plus or 7/2 plus. So before the before the last couple of years, I guess, what was known about these calcium-39 levels above the proton threshold came from this measurement by Matoba et al. In 1993 using the calcium-40 PD reaction. You can see their spectrum down here. But they found 3 levels in calcium-39 above the proton threshold, one at 6157, one at 6286, and one at 6460, all plus or minus 10 keV. So motivated by these discrepancies, the Dragon collaboration at Triumph decided to try and measure the potassium-38P gamma reaction directly using these energies that were found by the Matoba measurement to set the range that for their gas target. And so in this measurement, they only observed one resonance with an energy of 679 keV, which corresponds to the 6450 keV level. And they measured the resonance strength to be about 120 millielectron volts. The other 2 resonances they did not observe, but they were able to set upper limits on the resonance strengths for those 2 states. So a little bit more recently, the levels in calcium-39 were studied using, or by tunnel using their INGI spectrograph and the calcium-40 helium-3 alpha reaction. Here they observed 2 levels, one with an energy of 6154, which matches really nicely with the Matoba energy here, and one at 6472, which is somewhat significant because it's quite a bit higher than what was measured by Dragon. And so they mentioned in their paper that this would have been on the edge of the Dragon gas target. And so it's unclear if this is actually the energy for this level, if this resonance strength was measured accurately. And so to try and resolve at least some of the discrepancies and these discrepancy between these 2 energies here, we decided to take a look at this reaction channel in our Goddess data. So as I mentioned before, the setup and analysis here is very similar to what I talked about for Neon 19. In total, we found 32 transitions, with 23 of those being newly placed on the calcium-39 level scheme. So down here, I show our overall Doppler corrected spectrum, where each of these labeled states correspond really nicely to previously measured energies from levels in calcium-39 that was done using charged particle spectroscopy. So as you're looking at this, 3 of these might stand out to you a little bit, one being 6156, 6269, and 6471 states here. And so let's see how these energies then compare to those previous measurements. So of the levels seen by Goddess, 2 of them match really nicely with previous studies. The first being this one down here at 6156, which is only a couple keV different from the tunnel measurement. The next I'll point out is the highest one up here, where our energy that we measure is very, very similar to what was measured by tunnel, sort of supports their conclusions about the state. The middle resonance, as you're looking at, so this one wasn't actually measured by the Dragon or the tunnel measurements, but we find one at about the right energy, but it's a little bit lower than what was found by Matoba. And so this is also somewhat significant because it's possible then, so this would have been outside of the Dragon gas target range. And so it's possible that the upper limit for this resonance strength that they measured might also not be accurate. And so just to do a quick comparison, we varied the energies of these levels within their uncertainties and calculated the reaction rates, scaling the resonance strengths for energy that were found by Dragon. And what you can see here is that we really nicely reduce the uncertainty in the upper limit for this rate just based on the reduction in uncertainty on the resonance, on the resonance energy for this lowest level. As you look towards higher temperatures, you can see that this starts to kind of flick back up towards the previous measurements. And that's just due to the increased importance of this middle resonance here and its lower energy. Okay, so switching gears once again now to more specifically about solstice, and I'd really like to motivate the section, I guess, by asking how we might be able to do some of these experiments better. So one issue that we currently have that we kind of run into are with our targets. So in a lot of cases, you're trying to measure reactions using radioactive ion beams because you can't make a target out of the radioactive particle. And so some of these experiments that we really would like to do aren't possible with the low intensity of our radioactive ion beams and the background that you get from some of these target materials. And so if you want a proton or deuteron target, you're using something like polyethylene, which gives you a really nice background from the other components in the target. The other problem is that they degrade over time. You can see the damage from the beam from an experiment over here. In addition, if you want, for example, helium-3 or helium-4 target, you're constricted to using a gas target, so either a gas jet or a gas cell. Gas cells in general are somewhat problematic for very similar reasons to the targets because you need windows to hold the gas in. And so one way that we can get around some of these issues is to use a gas jet like JENSA, where JENSA is the jet experiments in nuclear structure and astrophysics. So currently JENSA is the SACAR target, but can also be used with detector setups like ORRUBA. So in general, what we're doing here is compressing our gas at about 30 atmospheres into our Laval nozzle. The gas then comes out at supersonic speeds, gets collected by a receiver cone, and sent back to the compressor. And what this ends up being, or ends up producing, is a jet with a density of about 10 to the 19 atoms per centimeter squared. So JENSA is currently installed on a dedicated RE3 beam line at the NSCL. And so I'll just talk really briefly, I guess, about one of the reactions that have been studied with JENSA, and so which is the neon 20 PD reaction. So this was actually done in normal kinematics at the Hallfield radioactive ion beam facility before JENSA was moved up to MSU. And so this was done by Bardayan and collaborators, which published a PLB and a PRC here. And they measured the neon 20 PD reaction to try and locate some important resonances in 4 and 18P alpha that I just talked about. And so one really nice thing that they did during this measurement was compared what you would measure with the neon jet with what you would get if you used a solid target, a neon implanted carbon foil target. And what you can see here is that they actually observe an important resonance for the 4 and 18P alpha reaction. It's a 1/2 plus subthreshold resonance. But as you're comparing both of these, you can see that this was really only possible because of the reduced background from the neon jet compared to the carbon target. And so problem 1 that I talked about was with our targets. Problem 2 that you kind of run into when you're doing these reactions in inverse kinematics is kinematic compression, where, so for example, for the silicon 28DP reaction, you can see that when you measure this reaction in normal kinematics, your protons, your proton energies doesn't really vary too much based on the lab angle that you detect them in, and your level spacing is basically preserved across all angles. Whereas if you're trying to measure this in inverse kinematics with a silicon 28 beam, you can see that the proton energies vary very steeply with lab angle, and the level spacing gets compressed down, and so you lose resolution there. And so the target effects really just exacerbate this poor resolution. And so just to give a quick example from some simulations done by Steve Payne for the tin 132 DP reaction, you can see that once your target is up close to, for example, 400 micrograms per centimeter squared, your target and beam effects begin to dominate over the detector effects. And so, and obviously, when you're measuring these reactions with really low cross sections, you want as thick of a target as you can possibly get. So you start to run into limitations there. So where our potential solution for the first was JENSA, our potential solution for the second is an orbital spectrometer like Helios at Argon, where here your beam is coming in, hitting your target, and your reaction products come out at backward angles, orbiting in the magnetic field and get detected some distance away from the target on axis. And here, so instead of measuring energy versus lab angle, you're measuring energy versus Z position, and your level spacing then gets preserved, and so you kind of recover that resolution. And so what we'd like to do with Solstice is combine both of these solutions into one device, where basically we're putting a gas jet like JENSA inside of the SOLARIS magnet, which will be at RIA 6 at FRIB, to take advantage of both of these solutions. And so there are some challenges and questions that kind of come along with this. One is that we can't run the pumps near the magnet, and so we need to figure out what effect this distance away from the magnet that will have to be will affect the pumping throughput, for example. Shadowing is also a big concern. As you can imagine with JENSA, you shadow quite a few of your reaction products from the receiver cone down here. And so can we reduce the shadowing then during design? And also, where does the shadowing show up in our detected spectra? And how does this impact the measurement? So SOLARIS itself is a very similar magnet to Helios. It's a little bit longer, I believe, but about the same diameter. It's a 4 Tesla solenoidal spectrometer that will be on one of the 2 RIA 6 beam lines, as you can see down here. So this is kind of an old picture now. I believe that they're starting to actually build the walls around it. And so we have a test setup at ORNL that we can use to try and test some of these effects. And so we have a large chamber to kind of simulate that solenoid volume, and a long pipe to simulate how far away from the solenoid we'll have to be to run our pumps. So our pumping setup right now consists of 2 root spoilers and 2 backing pumps. And as I mentioned, we can test what this effect on distance has on the residual gas pressure in the chamber. And so just to give you a little bit of information about our nozzle, so you can actually see the jet expanding into atmosphere on this picture here, which is pretty neat. But the inner dimensions of the nozzle are very similar, basically the same as the JENSA nozzle. And one really cool thing is that we have a new SLA 3D printer. So we might be able to actually print some of these nozzles, which will allow us to mess with the internal geometries a little bit, potentially in the future. We also have a new pumping system that was just delivered in June of 2020 to replace that old system here. These pumps are really nice because they're water cooled and have a single controller with built-in interlocks, which is really nice for FRIB, and have a greatly increased throughput compared to the old system. One issue that we have is that it's currently taller than the RIA 6 beam height, so this stand might need to be rebuilt. But also one really nice thing about this setup is that, as you can imagine, there are probably going to be some space constraints in the RIA 6 hall near the SOLARIS magnet, and so the footprint of this setup is actually relatively small compared to the pumps, being spread out on the floor. So a lot of the work that we've done has been to try and come up with a receiver cone that not only minimizes shadowing, but also keeps our chamber pressures at something somewhat manageable. And so when we're designing our receiver cones for Solstice, really you want the cone to be positioned as far away from the nozzle as possible to reduce shadowing. And obviously the geometry of the cone then affects what the pumping throughput is. And so if your receiver cone is too big, you end up getting back streaming out of the sides from the jet. Whereas if your cone is too small and too far away, you end up just missing the cone entirely. And so the situation that we were in when I first started at Oak Ridge was our best cone was this blue one here, which was originally designed by Holly Stemp. But it was only about 1 inch away from the nozzle. As you can see, the pumping curve down here based on the jet pressure. And so we really needed something that would shadow our reaction products less. And so we were able to 3D print these cones, which allowed us to really rapidly design and test them, and also test some geometries that are that would be really difficult to machine. And so the best cone that we ended up with actually was this one down here, which for some reason is the best shape by about 100 millitorr compared to just your straight sides traditional cone over here. This one has an opening diameter of about 2.6 inches and is 3.75 inches away from the nozzle, so significantly farther than this blue cone here. And it actually provides pressures very similar to what this blue cone does. So we decided to also try and print the nozzle infrastructure. So you can see just a cool little time lapse down here of one of these parts being printed. But what we really wanted this to be was movable for alignment and non-magnetic, and reduced amount of material for the shadowing. So you can see over here a few of the pictures that I took as I was kind of putting this thing together. As I mentioned, we want it to be movable, so we have these plastic ball bearing tracks that we can use to move it around, which is really nice. So this is what it looks like kind of in the chamber over here, where we can align it horizontally and vertically, which is really great. And we have that 3.75 inch distance from the nozzle here. So this is what that might look like inside of the SOLARIS magnet. Here we've actually reduced the length of these arms and added a couple of targets that we might be able to put in and use. But just to give you an idea, so as you can imagine, we really needed to come up with a particle shadowing simulation code to really be able to see where the shadowing ends up, because it's somewhat unintuitive. And so in the simulations that I'm about to show, we use the silicon-28 DP reaction, as I talked about a little bit before. And what this shadowing code really allows us to do is alter the design if we need to when we make, based on the amount of shadowing that we get. And so if you're familiar with the spectra that you get from the Helios detector currently, you get something that looks like this, where you're measuring your energy versus your Z position, and each of these lines correspond to a state in silicon-29. And so we can use the simulation code to then guide the setup design, where we can make these contour plots that show the fraction of particles detected. So as you can imagine, as you get closer to the nozzle and the receiver cone, you have more particles hitting you have more particles, I guess, hitting both of those things and stopping. And so here you're detecting something like 25% of your particles, whereas further away at angles closer to 180 degrees, you're detecting all of them. And what's really nice is that we can break these up into the individual components, so shadowing from the nozzle, and shadowing from the gas pipe, and shadowing from the receiver cone individually. And so if we make any changes to these geometries, we can then use the simulation code to really check and see what the differences end up being. And so just to end with, how much better is our new cone compared to this blue one? So the down here I have plotted the shadowing from or based on initial phi angle versus lab angle. And you can see this lobe up here is from the shadowing from the nozzle, which is at 90 degrees. And the shadowing down here is from this receiver cone. And when we compare that to our new receiver cone, you can see that the nozzle shadowing is exactly the same as you would expect, but the shadowing from the receiver cone is greatly reduced down to about less than 110 degrees in the lab frame. And so this was a really nice, I guess, step in the direction that we wanted to go. Okay, so just to summarize, measuring reactions that are important to constrain nucleosynthesis in explosive stellar environments. And we really need both direct and indirect measurements, and both kind of have their own unique challenges. I talked about the fluorine-19 helium-3T and calcium-40 helium-3 alpha reaction measurements that we did with GODDESS to get information on the fluorine-18P alpha and potassium-38P gamma reaction rates that are important for novae. And as I mentioned, it's difficult in some cases to get information using our traditional targets with inverse kinematics. And so one thing that we're trying to make is SOLSTICE, which is a gas jet target inside of a solenoidal spectrometer. SOLSTICE is still really under construction, and obviously there are still a lot of questions that remain unanswered here. So I'd just like to thank all of my collaborators, and I'll go ahead and take your questions.
Yeah, thank you, Matt. I see one question in the chat from Lisa Buttons. If Lee wants to unmute himself. If you're there, Lee.
Okay, do you hear me?
Yes.
Yep.
Sorry, this was so long ago now that so I guess it was the neon 19.
Mm-hmm.
And you had a case of 2 photons. One was, I guess it was very long-lived, that was interfering with another, and so you couldn't say anything about it. But your words seem to imply that you only had Doppler shifted or non-Doppler shifted, but in fact you have both, and you could not Doppler shift, see the things in that count, in that peak that I think was 10 keV, or anyways, it was far away peak, and just eliminate them. So I didn't see that when you said that they were overlapping and you couldn't remove it. I didn't understand why you couldn't remove it.
Mm-hmm. Yeah, so I sort of left out a couple of the details here. So this 1840 keV, let me put this back full screen. This 1840 keV gamma ray is coming from a level at I forget the energy, it's like 4,500 or so keV in neon 19. And there is actually a really intense gamma ray from a state at 6288. And so you can see that decays to that level. And so the 1840 is present in this triton gate, which is why we weren't able to see decay from these two 6400 keV states, if that makes sense.
No, you lost me, but it's okay.
Yeah, so basically there were 2 levels in neon 19 that didn't need the Doppler correction, and so the problem is that once you do the Doppler correction, all of the states that needed it, their resolution, is really nice, but all the states the couple of states that didn't need it, the gamma rays from those just get smeared out.
No, I understand that, but yeah. Again, you're going into a language that presumes you have one or the other, but you have both. So you can look, right. In any event, you can look. Okay, let's let it go.
Okay, yeah. If you want me to explain it a little bit better to you, go ahead and email me, and I can get back to you on it.
All right, thank you.
Mm-hmm. Okay, do we have any other questions? You can just go ahead and unmute yourself and ask Matt. Oh, Philip.
Hello, is that working?
Yes.
Yep.
Great. So I have 2 questions.
Okay.
And sorry, I wrote them at the back of my hand, and my handwriting is very bad. So, okay. So the first one is: have you tried looking at? Is it possible to look at the angular correlations of the alpha particles and the gamma rays? And can that tell you anything about multipolarities?
Yeah, so that's one thing that we've kind of thought about as kind of a next step for the analysis for this one, I guess. Yeah, it's something that we could do in the future, yeah.
Okay. And the second question I have is, so we're actually planning on remeasuring the Matoba PD data on calcium-40 to try to resolve some of these questions to see
Sure.
whether there's maybe things lingering in those data which are problematic. But
Yeah.
are there one of the questions that I've not been sure about with the tunnel data, because they're using helium-3 alpha, which tends to favor higher spin, versus PD, which favors lower spin. Is there any evidence that you've seen of that the spin selectivity has been a problem with these or any other selectivity for the states of as to a possible
For the helium-3 alpha?
Well, for the discrepancies, but between the helium-3 alpha, the PD, the P gamma.
Yeah, so at least in our data, it looked like, so obviously these aren't all of the gamma rays that we found, but it looked like we were populating basically every spin parity level in calcium-39. It didn't really look like there was, any selectivity towards the higher ones compared to the lower ones. But it also could be that the gamma rays for some of them are more intense than others. So, it's sort of hard to say
Okay.
either way. But.
Thanks.
Mm-hmm.
So any other questions for Matt?
Kate, I have a question. This is Grisha.
Oh, go ahead.
So your jet seems to be rather large now because you move nozzle down, right, to create this gap. And the physical dimension of the jet is rather large. Does that induce some uncertainty, additional uncertainty on scattering angles in particular?
Yeah, so, oops, something just fell over there. So we're actually still going to be measuring these about 2 or 3 millimeters below the nozzle before the jet blows up. And so the beam height would be somewhere right around here. And so in the particle shadowing code, we've also included beam spot size and jet diameter and stuff in the simulation, and it ends up still being slightly or a little bit better than solid target in terms of the position resolution and stuff.
Okay, thank you.
Yep.
I have a rather naive question about the Doppler correction.
Mm-hmm.
So can't you do the Doppler correction not as a function of the velocity of the emitting nucleus and find for each peak what the best velocity is? So all the peaks that are associated with the same nucleus should in fact have the same average Doppler frame of reference. And that way you wouldn't be having to choose between either no Doppler correction or the Doppler correction associated with one particular choice.
Yeah. Yeah. So it's possible that there was a better way to handle the Doppler correction. In general, one sort of nice thing about doing a reaction inverse kinematics is that your velocity is essentially the same, and the particles are only going in one direction. But for this normal kinematics measurement, the velocity really depended on the angle that the triton was detected at. So I'm not sure that we would have been able to do something like that, come up with just a single velocity for this. But it's possible I'm not thinking of something correctly either. So.
Thanks.
Any other questions? If not, I would like to thank Matt again. I'll clap for everyone, and invite you to come back October 1 to see Daniel Hoff give his presentation. So thank you, everyone. Thank you for coming, and we'll see you in a couple of weeks. Thank you, Matt.
Yep, thanks.